Okay, so get this. The Nobel Prize in Physics. It was just awarded for groundbreaking work, but in artificial intelligence.
Uh-huh.
You heard that right, physics and AI.
Yeah.
It's not exactly the usual pairing, is it? Which is exactly why we are diving into this today.
Yeah, it's pretty
We're
whack.
talking about the physics behind artificial neural networks and how two scientists, John Hopfield and Geoffrey Hinton, completely revolutionized the field.
What's so fascinating here is that this connection between physics and AI, well, it isn't some recent, groundbreaking discovery.
Right.
It's been there all along, just hidden in plain sight.
So let's start with the award itself.
Okay.
John Hopfield and Geoffrey Hinton, their work on artificial neural networks just won them the 2024 Nobel Prize in Physics. Now, I don't know about you, but when I hear physics prize, I don't automatically think AI.
Right.
It seems like there's a story here.
You're right, there is. You see, John Hopfield wasn't even trying to change, the world of computer science or anything.
Right.
He was busy exploring this fascinating area of physics, something called spin glasses.
Spin glasses. Okay, now you've got my attention. What are those?
Okay, so just picture a bunch of atoms, each one acting like a tiny little magnet.
Okay.
But here's the thing. They're all jumbled together, interacting in these really complex and unpredictable ways. That's a spin glass. Now, what's incredible is that Hopfield saw a connection between how these spin glasses behave and how our brains might actually store memories.
So you're telling me that studying these messy, unpredictable atomic magnets, that gave Hopfield the idea for a learning machine?
Yeah,
That's wild.
it is pretty wild.
What did he do with this connection?
So that connection led him to develop what we now know as the Hopfield network in the early 1980s.
Okay.
So imagine a network of nodes, kind of like a web. Think of them as pixels in an image, all connected with these varying strengths, like synapses in the brain.
Okay, I'm picturing this web of interconnected nodes. What makes it a learning network?
Okay, here's the key. The network learns by adjusting those connection strengths to store specific patterns. Let's say you feed the network a bunch of images of cats.
Hmm.
The network learns to associate certain patterns of pixels with cat by fine-tuning the strength of connections between those pixels.
So it's almost like the network is building a memory of what a cat looks like based on these pixel patterns.
Yeah.
But how would that help us in practice?
Let's say you then give it a noisy or an incomplete picture of a cat, maybe just the tail and an ear.
Right.
The Hopfield network, by adjusting those connection strengths, can actually complete the picture, revealing the full image of the cat it's learned.
Wow, that's incredible.
It is pretty amazing.
It's like the network is filling in the blanks based on what it's already seen.
Yeah.
So it can recognize even incomplete images.
Mhm.
Is that basically how our brains recognize things too?
That's the idea Hopfield was exploring. And this whole concept of storing patterns, it borrows directly from the physics of those spin glasses. Think about how a ball will naturally roll downhill to its lowest energy state. The Hopfield network works in a similar way, adjusting itself until it reaches the lowest energy configuration that represents the stored pattern.
Okay, so we've got these networks storing information as low energy states.
Mm-hmm.
This is already blowing my mind, and we haven't even gotten to Geoffrey Hinton yet, right?
Right. That's where we delve into another fascinating area of physics, statistical physics, which is where Hinton's work comes in. But first, maybe let's take a quick break.
And we'll be right back with more on this fascinating intersection of physics and artificial intelligence. Don't go anywhere. All right, so we're back, and last we left off, you were about to tell us about Geoffrey Hinton and his connection to something called statistical physics.
Oh, right, yeah. So Hinton comes along in the late 1980s, a computer scientist, and he kind of took Hopfield's ideas in a whole new direction. He was fascinated by this different branch of physics called statistical physics, and instead of looking at individual atoms like in spin glasses, this field kind of zooms out to deal with systems with tons of similar components. Think of all the molecules in a gas, each one moving around and interacting with each other.
Okay, so lots of tiny things interacting. I can see where the connection to neural networks, might be there, but how do you actually use that to, teach a machine?
Yeah, well, that's the genius of Hinton, right?
Yeah.
He realized you could use the principles of statistical physics to create a whole new kind of learning machine, and he called it the Boltzmann machine.
Okay, another network, another brilliant mind. What makes the Boltzmann machine different?
So the Boltzmann machine learns differently. Imagine, instead of just memorizing specific pictures of cats, you give the machine a crash course in what makes a cat a cat.
Okay.
You show it all kinds of cats, different breeds, angles, lighting, you name it, everything. And the machine starts to learn the underlying probability distribution of catness.
So instead of just recognizing a pattern it's seen before, it's learning the general rules of how cat pictures are usually structured.
You got it. And that's a game changer. It means the Boltzmann machine can do a lot more than just, complete patterns. It can classify data into different categories, like telling you this is a cat, this is a dog, and it can even generate totally new images based on what it's learned about catness.
Wow. So it's going from recognition to creation. Like it understands the essence of a cat.
Exactly.
This Hinton guy was way ahead of his time. But how does this actually work? We talked about nodes and connections with Hopfield networks. Do those still apply here?
Absolutely. Both Hopfield networks and Boltzmann machines have those interconnected nodes, but what's different is how they learn. To really understand that, we need to talk about how the networks actually find those low-energy states, which, as you might remember, represent the stored patterns or correct classifications.
Okay, so it's not just about storing information. It's about finding the best way to store it, the most efficient way.
Exactly. Think of it like this, okay? Imagine a ball rolling down a hill.
Okay.
It naturally wants to find the lowest point, its lowest energy state, right?
Right.
Hopfield networks and Boltzmann machines work in a similar way. They want to reach that lowest energy state, which represents the stored pattern or the correct classification. But they have different words of actually getting there.
So both are trying to roll down the hill, so to speak, but they're taking different paths to get there.
Precisely. We call these paths learning rules.
Okay.
And they determine how the network adjusts those connection strengths or weights to kind of nudge itself towards the lowest energy state. It's like giving the ball little nudges to help it roll down the hill more efficiently.
Okay, I'm starting to get the hang of this. So we've got the nodes, the connections, and now these learning rules that guide the network to the lowest energy state. But you also mentioned something called activation functions earlier. What are those all about?
Ah, yes. Activation functions dictate how each node in the network responds to its inputs. It's kind of like a light switch. If the input is strong enough, it flips the switch on, activating the node.
Right.
If not, the node stays off.
So the activation function is like a gatekeeper, deciding which nodes get to contribute to the network's overall decision-making process, so to speak. And those decisions ultimately influence the whole network's energy and whether it gets to the right answer, the lowest point on that energy landscape. This is getting pretty nuanced. I bet even seasoned computer scientists find this challenging.
You'd be surprised. There's actually this dance between energy states, learning rules, and activation functions that make these networks so powerful. But you're right, it gets even more interesting when we consider the specific ways Hopfield networks and Boltzmann machines differ.
Okay, so we've got these two incredibly powerful networks, both drawing inspiration from physics, both trying to reach that lowest energy state, but through different paths. What's the upshot here? How do those differences actually play out when we talk about what each network is best at?
Yeah, that's the million-dollar question.
Yeah.
And it goes back to those specific challenges these networks were designed to tackle. So Hopfield networks, with their focus on storing specific patterns, they're masters of completion.
Okay.
You give them part of a pattern, remember that cat image,
Right, right.
and they can, through that whole process of minimizing energy, fill in the rest.
Which makes sense, right?
Yeah.
They're trying to reach that
Right.
stored low energy state, even if they only have part of the puzzle.
Exactly. But Boltzmann machines, because they're not just storing specific patterns, but learning the broader rules and relationships within the data, that probability distribution we talked about,
Right.
they can do so much more.
Right, they're not just remembering, they're understanding on a deeper level, like the difference between memorizing a painting and learning to paint yourself.
Got it. And that's where their versatility shines. They can classify data, telling you this image is more likely to be a cat than a dog. And they can even generate totally new examples that fit the patterns they've learned.
So Boltzmann machines are less about recreating a specific memory and more about understanding the underlying system that generated that memory.
Perfectly put. And this ability to understand and create, that's what makes them so incredibly powerful for a wide range of applications that we see today. Things like image recognition, natural language processing, even drug discovery.
It's mind-blowing to think that something inspired by the physics of how atoms interact could lead to such incredible breakthroughs. But speaking of breakthroughs, we can't forget why we're talking about all of this in the first place. This wasn't just a theoretical exercise. This work just won a Nobel Prize.
Absolutely. And that speaks volumes about the impact of Hopfield and Hinton's work, right? The Nobel Committee, they weren't just celebrating the elegance of the theory. They were recognizing the very real and tangible effects these networks have had on the world.
You mentioned applications across various fields. What are some concrete examples where these networks are making a real difference?
Well, you mentioned it earlier, healthcare. Researchers are now using artificial neural networks, particularly those building on Hinton's work with Boltzmann machines, to predict cancer using what we call multimodal data.
Okay, multimodal data. For those of us who aren't doctors or scientists, what does that actually mean?
So it means instead of just looking at one type of information, like, say, a medical image, you're combining several different types of data. Medical images, genetic information, patient history, and you're feeding it all into the network.
So the network is getting a much richer, more holistic picture of the patient's health.
Precisely. And by training on this multimodal data, the networks can learn to identify very early signs of cancer, even when those signs might be missed by human eyes. It's like giving doctors a superpower, helping them diagnose and treat patients more effectively.
That's incredible. We're talking about potentially saving lives with technology inspired by the physics of tiny interacting particles.
It really highlights the interconnectedness of everything, doesn't it? And this is just one example. We're seeing similar breakthroughs in material science where these networks are being used to design new materials with tailored properties.
It makes you wonder what other frontiers we can push when we embrace this kind of interdisciplinary thinking. If studying spin glasses can lead to breakthroughs in artificial intelligence and healthcare, what else might be possible when we bridge the gap between these seemingly disparate fields?
That's the beauty of science and exploration, right? Every answer opens up a dozen new questions, pushing us to delve deeper, challenge our assumptions.
It's really amazing stuff and a perfect note to end on, I think. So to our listeners out there, thank you for joining us on this deep dive into the fascinating world of physics and artificial intelligence. Until next time.